Hello, welcome to my physics YouTube channel. Today we are going to be looking at vibration in strings and vibration in air column. But before we go ahead to do that, I want to take us through the waveform because that will help us to understand the formulas very well and how to go about deriving the formulas for the stretched string and the formulas for vibration in closed pipe and open pipe. Now look at the diagram that you have before you. This is the diagram of a waveform. You can see the wave going from the point A all through to the point G. Now the distance between A to E is equivalent to one wavelength. And talking about wavelength, what is a wavelength? A wavelength is the distance of one complete oscillation. The distance covered by one complete oscillation, or the distance covered by a complete circle, or the distance made by a complete circle in a wave. So the point A to the point C is equivalent to half of a wavelength, and the point from point C down to the point E is also equivalent to half of a wavelength. So a wavelength can be said to be the distance between successive troughs or successive crests. Now talking about successive crests, the point B and the point F, the distance from point B up to the point F is equivalent to one wavelength, because from point B to point C is quarter of a wavelength, and from point C to point E is equivalent to half of a wavelength, and from point E to point F is equal to what? Quarter of a wavelength. And if we add a quarter plus half plus 1/4, that will give us one wavelength. Now the wave equation is V equals F lambda, where our V is the speed or the velocity of wave, and our F is the frequency of the wave, and our lambda is the wavelength of the wave. So we can say that the speed or velocity of a wave equals to frequency of a wave times the wavelength of the wave. Now we move straight to vibration in strings. Now considering the diagram that we have above, you can see a string tied at both ends, at the point X and at the point Y. If the string is plugged at the middle, there will be a vibration that will be set in across the string. Now the least vibration, which is known as the fundamental note of the vibration, gives us what we have in the diagram. So for this, you can see that the wavelength traveled by the wave is equivalent to half, because we are looking at we are taking note of the green line and not the green and the black line. It's just like that because when it is vibrating, it looks as if it is two, but in the real sense, it is just one string. But when the vibration dies down, you see that it is one string. So the distance covered by this fundamental note is equivalent to half of a wavelength, and the length of the string is equal to L. So we can say that the length of the string for the fundamental note is equal to half lambda. So if we make lambda, which is the wavelength, subject of formula, we'll have that the lambda equals to 2L. Now from the equation of wave motion, which is V equals F lambda, we can write V equals F naught times 2L, where our F naught is the fundamental frequency of the note produced, then multiplied by 2L, which is the value of our wavelength as we have seen above. And if we make F naught the subject of formula, our F naught will be equal to V over 2L. So the fundamental frequency is equal to the velocity of the wave over 2 times the length of the string. In this diagram, the vibration in the string has gone beyond the fundamental note, and it has extended up to the first overtone. And this gives us a second harmonic. Harmonics are multiples of the fundamental frequency. Now in this diagram, you can see that the length of the string still remains L, but the wavelength produced is equivalent to 1 wavelength. If we look at the distance, trace out the green line from X to the point where the green line and the black line meet. It's equivalent to what? Half of a wavelength. That green line still continues and up to the point Y. That gives us another half of a wavelength. So half of a wavelength plus half of a wavelength gives us 1 wavelength. So that means that the length is equivalent to 1 wavelength. So from V equals to F lambda, we can write that V equals to F1 lambda, where F1 is representing the first overtone. So if we make F1 the subject of formula, then we can say that F1 equals to V over lambda, and that is equals to V over L, because lambda equals to L, and that is equivalent to 2 F naught, because our F naught, which is the fundamental frequency, equals to V over 2L. So if we say 2 times V over 2L, that will give us V over L. So the first overtone is equal to the second harmonics, because I said earlier on, harmonics are multiples of the fundamental note, and the fundamental note in this case is what? F naught. And then we look at another scenario where the vibration has increased and it has produced 2 more overtones. So this gives us the second overtone, and the length of the string still remains L. But the wavelength now, if you trace out the green line, you can see that we have 1.5 wavelength, and that is equivalent to 3 over 2 lambda. So our length, our L, is equal to 3 over 2 lambda. So if we want to make lambda the subject of formula, we can say 3 lambda equals to 2L. So our lambda equals to 2L over 3. Once again, let's recall that velocity equals to frequency times wavelength, V equals to F lambda. So in this case, we are looking at the frequency, looking for the frequency of the second overtone. So we can say V equals to F2 lambda. So our F2 equals to V over lambda, and our lambda is equal to what? 2L over 3. So if we substitute the value of lambda, which is 2L over 3, into this formula for lambda, we have that F2 equals to V divide 2L over 3. So if we do our arithmetics, we'll have that F2 equals to 3V over 2L, and that is equivalent to 3F naught, because our F naught is equals to V over 2L. So the second overtone is equivalent to the third harmonics. Once again, I said that the harmonic is the multiple of the fundamental frequency. So our second overtone is equal to the third harmonic. Next, we'll talk about vibration in air column. And an air column is defined as air in a tube. Now, we can have two different types of tube or two different types of air column. We have what we call the open pipe or the closed pipe. For the closed pipe, the pipe is closed at one end and open at the other end. At the end closed, you have an antinode for the vibration, and the open part has an antinode. For the open pipe, both ends of the pipe are open, as you can see in the diagram, and is characterized by antinode at both ends, and you have the node in between. So this gives us the fundamental note for an open pipe. Now, if you look at the diagram also, the length of the vibration in the open pipe is equals to L, as you can see by your left. Now, the distance of the wave from X to Y is equivalent to half wavelength, which is lambda over 2. How did we get that? From X to N is equivalent to a quarter of a wavelength, like I explained at the beginning of this class. Then from N to Y is also equal to a quarter of a wavelength. So a quarter plus a quarter gives us what? Half wavelength. You can also see that between an antinode and a node, you have a quarter of a wavelength. And between a node and an antinode upward, you also have a quarter of a wavelength. So the distance between two successive nodes is equivalent to what? Half a wavelength. And the distance between two successive antinodes is equivalent to what? Half of a wavelength. Now, since our length, the length of the air in the tube or the pipe is equal to lambda over 2, we can say that the lambda, which is the wavelength, equals to 2L. So from the wave equation, V equals F lambda, and we are looking for the fundamental frequency of the note. So we have that our F naught equals to V over lambda. So our F naught will be equals to V over lambda is equivalent to what? 2L. So F naught equals to V over 2L. The first overtone. Now the diagram we have illustrates what we have, the vibration for the first overtone. Now you can see that we have the length still remaining L, but this time around we have an overtone that is between N and the other N. So L, which is the length, still remains the same. The distance of the vibration, taking the distance from X up to Z, is equivalent to 1 lambda, that is 1 wavelength. From X to N is equivalent to half of a wavelength. From N to Y is equivalent to from X to N is equivalent to a quarter of a wavelength. From N to Y is equivalent to a quarter of a wavelength. From Y to N is also equivalent to a quarter. And from N to Z is equivalent to a quarter. So if we add up the quarter plus quarter plus quarter plus quarter, that gives us 4 quarter, which is equivalent to what? 1 wavelength. So the length is equivalent to a wavelength. So if we bring in the equation of motion of wave, we have that V equals F1 lambda. So our F1 equals to V over lambda. And our lambda is equals to L. So we can say that the frequency of the first overtone is equal to V over L. And that is equivalent to what? 2F0. Because our F0, which is the fundamental frequency, is equals to V over 2L. So 2 times V over 2L will give us V over L. And that's why we say that the first overtone is equal to what? The second harmonics. Remember once again, an harmonic is a multiple of the fundamental frequency. Now let's look at how we derive the formula for the second overtone. Now look at our diagram for the open pipe once again. We have 2 overtones. The length still remains L. Now the wavelength is equivalent to 3 over 2 lambda, that is 1.5 wavelength. How did we arrive at that? Between W and N is a quarter of a wavelength. Between N and X is also another quarter of a wavelength. Between X and the upper N is equivalent to what? A quarter of a wavelength. And from N to Y is also a quarter of a wavelength. From Y to the upper N is also equal to a quarter. And from N to Z is equal to a quarter of a wavelength. So if we add a 1 quarter plus 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 1 quarter is equal to 3 over 2 lambda. Alternatively, we can say that the distance from W to Y is equal to 1 wavelength. And from Y to Z is equal to what? Half of a wavelength. So 1 plus 1 over 2 gives us 3 over 2 wavelengths. So we now say that our length of the air column is equals to 3 lambda over 2. To make lambda the subject of formula, we have 3 lambda equals to 2L. Then lambda equals to 2L over 3. So recalling again the equation of motion, V equals F lambda. And this time around, we are talking about the frequency of the second overtone, F2. So our V equals F2 lambda. So if we make F2 the subject of formula, we have that V over lambda equals to 3V over 2L. Because our lambda is equal to what? 2L over 3. So that means that the frequency of the second overtone is equivalent to what? 3F0, that is 3 times the fundamental frequency. Why? Because fundamental frequency, as we have seen, is equal to V over 2L. So we have the second frequency of the second overtone to be 3F0. And as we round up, we'll look at the closed pipe. Once again, we said that the closed pipe is a air column in air in a pipe in which one end of the pipe is closed and the other end of the pipe is open. Now, the fundamental note that is produced is what you can see in the diagram above. At the first resonance, you have a node and an antinode. Now, the length of the air column is given as L, and you can see that the vibration produced is equivalent to a quarter of a wavelength. That is, from N to X is equivalent to what? A quarter of a wavelength. So we can say that the length of the air column equals to lambda over 4. So our lambda is equal to 4L. So once again, from the equation of wave, we have V equals F0 lambda. So F0 will be equal to what? V over lambda. and that will give us V over 4L because lambda equals to 4L. So the frequency, the fundamental frequency of the vibration in a closed pipe is F naught, and that is equals to V over 4L. Next, we want to look at the frequency. How do we derive the frequency of the first overtone? Now, with our diagram, we can see the first overtone formed already. The length still remains L. Now, the wavelength going from N at the closed end of the pipe up to Y is equivalent to 3 over 4 lambda, because between N and another N we have half wavelength, and from N to Y we have a quarter of a wavelength. We are looking at using the green line, yeah. So our L equals to 3 wavelengths over 4. So if we make lambda, which is the wavelength, the subject of formula, we have lambda equals 4L over 3. So recalling again the equation of wave, we have V equals F lambda, and now our F is the frequency of the first overtone, so we represent it as F1. So making F1 the subject of formula, we have F1 equals V over lambda, and that is the same thing as V divide the value of lambda, which is 4L over 3, and that means that our F1 equals 3V over 4L, and that is equivalent to 3F naught. So the first overtone for the closed pipe is equivalent to the third harmonics of the fundamental frequency. Now we want to look at how we derive the formula for the frequency of the second overtone for a closed pipe. Now we have our diagram again, and this time around we have the second overtone formed in the closed pipe. The length of the pipe still remains L, and then the wavelength going from N to X using the red line from N to X is a quarter of a wavelength. From X to N is also a quarter. From N to Y is a quarter. From Y to N is a quarter. And from N to Z is also another quarter of a wavelength. Alternatively, between the N at the bottom of the closed end of the pipe and the N to at the top, the top of the pipe, you can see that the wave has traced a complete wavelength. That is, it has gone from N to X to N to Y and then to N. That is a complete wavelength. So that is 1 plus a quarter of a wavelength, which is formed from N to Z. So 1 plus 1 over 4 gives us 5 over 4 lambda. So we say that the length equals to 5 lambda over 4. So if we make lambda the subject of formula, we have lambda equals 4L over 5. So recall again the equation of wave, which is V equals F2 F lambda. And now we are looking for the frequency of the second overtone, and that's why we have it as V equals F2 lambda. So if we make F2 the subject of formula, we have F2 equals V over lambda, and that is equals to V divide the value of lambda, which is 4L over 5. And that means our F2 equals 5V over 4L, and that is equivalent to 5F naught. So the second overtone is equal to the fifth harmonic of the fundamental frequency. That is the fifth. The harmonic is a multiple of the fundamental frequency. So F2 equals to 5F0.